असतो मा सद्गमय तमसो मा ज्योतिर्गमय मृत्योर्मा अमृतंगमय। ॐ शान्ति शान्ति शान्तिः।
Namaste. In this video, we continue with instantaneous velocity. In fact, in today's video, we learn how to exactly calculate the instantaneous velocity, what was solved 360 years back by Newton. And thereby, we enter into a new mathematical era, what we call as differential calculus era. So now we start with that idea. Till that point of Newton's life, nobody before that, no scientist has thought of these ideas. In fact, that is the starting point of what we call as differential calculus. Now, we consider this situation. An object is moving, say, on a path like this, I consider 2 points on it. I consider 2 points, A and B. At A, the velocity will be like this, what we call as VA. And at B, the velocity will be like this. But what we want is to know velocity at A. To know velocity at A. How to do that? That's what is our today's thing to learn. For that, observe. Once we observe the object at A, by the time we look at it, it moves to B. Then it has displaced through delta x1, I say. In time, delta t1. Then if I calculate the ratio, what I get as V1 as delta x by delta t1, delta x1 by delta t1. But our aim is to get velocity exactly at A, what we call as VA. How to do that? So here, for the sake of clarity, I take delta t is 0.1 second. 0.1 second. In the next idea, what I do, what I want, the velocity at A. So I have to look exactly at A. But once I look at A, and by the time we look at the next thing, it moves forward. So what I do now? Next, I take the same path, but what I do now? At A, as it is, there's nothing change. We write it as VA. But now we look at B, that is, we look at the path and the object very quickly, then delta T1. I say delta T1 is 0.0, delta T2 is 0.01 second. That means smaller, 1/10 smaller than delta T1. Now, what will happen? Observe carefully. This will be somewhere here, delta VB, and that will be VB. But even now, if I take the ratio delta x2, that is the distance between this delta x2 by delta t2, even it will not give me exactly at A. Now, observe carefully. In the next situation, I write the same path, but now we further reduce A to B time gap. That means, as soon as we see A, we look at next position very quickly. B means the next position in all these things. Say, we take this A and this is our VA as usual. But observe, I want to see the B here only, very near to A. Now the time gap is further reduced, what I call as delta T3, 0.001 second. Now V3 I write delta x3 by delta T3, where delta x3 is this one, A to B gap, delta x3. Observe, as we go on decreasing the time, zero point 0.1 to zero point 0.01, B can become very near to A, and zero point 0.01 to zero point 0.001, B become much nearer to A. If I go on doing like this, if I go on reducing delta t time interval, very smaller, what can you think? The gap between A and B goes on decreasing. But what situation I want to say, we measure delta x1 almost at the same time. What does it mean? Delta t, the time gap, should be very small. How much? Almost zero, but not zero. Almost zero, but not zero. If it is zero, then there's nothing to measure, and we cannot do the measurements. So almost zero, but not zero. That's what I write in the next moment. I cannot write A and B separately now. Just observe, I write it like this. This is our A and VA, and I cannot write delta T is almost small. Say at B, almost there. VB. Now the delta T, I write only simply delta T is almost zero, but not zero. That's why I write delta T tends to zero. That arrow mark is to be read as tends to zero. That means it is going nearer to zero, but not becoming zero. Going nearer to zero, but not becoming zero. Likewise, say sometimes here I remember one beautiful thing. Sometimes some villages in India say whenever they have to show, when we ask them to show the route for a particular place in their village, they say for a particular field or something like that, they say, sir, it's here, come. By saying that, they make us to walk more than 1 kilometer or 1.5 kilometer. Whenever we ask, sir, it is here only. But we have traveled 1.5 kilometers or like that. But here that is not the case. We are reducing the time smaller and smaller. How much smaller? Almost zero, but not zero. So that's what is the idea now. Then, how do we write this? Then I write V as with a special symbol limit delta x by delta t as delta t tends to zero. Observe, to be read as I read. Limit delta x by delta t as delta t tends to zero. That ratio is calculated when delta t is approaching zero, almost zero but not zero. So this is what does give us the velocity at A, that is instantaneous velocity. In fact, this what we have calculated, what we have written here, V limit delta t tends to zero, delta x by delta t. You can, if you want, you can make it as a vector. You can write it as a vector by writing vectors on delta x and V. At that moment, delta t tending to zero. Observe, always I am using tending to zero, not zero. Okay, then that overall right hand side is what we call as differential of x with respect to t, and that gives us the velocity at that instant. What is that? Actually, this whole thing can be simply say written symbolically dx with respect to t. It's a symbol to represent limit delta x by delta t as delta t tends to zero dx by dt. It's not d separate x separate d separate d. No, it's a symbol for that. This is what we call as differential of x with respect to t. It was created by Newton, and the notations what we are using here by Henry Leibniz, the contemporary of Newton. And this is what we call as instantaneous velocity. This is how we calculate. There are some formulae in the calculus, differential calculus, We by applying those things, if the path of the particle, we can calculate the instantaneous velocity. I'll show it a little later. Now observe. So what all we learned, as we go on decreasing the time interval to make it zero but not zero, tending to zero, make it smaller and smaller but not becoming zero, then we get what we call as the instantaneous velocity. This is the mathematical procedure, and we need not do all these things again and again whenever we come across a numerical in physics. There are some numerical formulae, and we apply, we get it. But this is the basic thing behind differential calculus from the point of view of physics. Okay, there I conclude this video. I'll come up with some more things with these differential calculus ideas in due course. Thank you.